All right, so coming back into part two of the video, kind of recapping where we were, we had done two properties of definite integrals. One that you can break a definite integral into subcomponents and then add them up. The second one is that you can reverse the order of a definite integral, that there's a forwards and a backwards. And that if you're going backwards, quote unquote, through the integral, then it is the opposite of what happened before. So if forwards was accumulate or positive, then going backwards is deaccumulate or negative, kind of like VHS tapes and rewinding. But the combination of these two together is also that I wanted to come back in here and talk about the fact that the number that is here, the B, that's here and here, there is a fact, and it's because of the combination of the first two properties. B does not have to be between, does not have to be between A and C. And it also does not have to be left or right of, like, it doesn't have to be like the forward and reverse that I was talking about from A to B. You could have B being 0 and A being 5, or you could have B being 5 and A being 0. It doesn't really matter order on these things, that these properties work both ways. That if I have 5 to 0, that's the same as the opposite of 0 to 5. And just like negatives, you can move them from one side to the other. So it doesn't really matter that the negative is in front of the left side or the right side of that equation. Likewise, B does not have to be between A and C. Let's come back up to our graph that's right here. And let's think about kind of this idea of moving forwards and moving backwards. What if my B, like I wanted to do the definite integral from, say, 12 to 20 of f of t dt. Now, I wouldn't necessarily do this. Obviously, I would just add the two areas up, and then we would see that that's equal to 108. So we know that that answer is 108. But watch, I can actually do this by going forwards and backwards as much as I want to. So I can actually do the integral from 12 all the way out to 24 of f of t dt. Add that to the integral from 24 back to 20 of f of t dt. And what that would show me kind of as I am doing that, 12 to 24 obviously would be the 48 plus the 60 plus the 36. And then 24 to 20, well, that's going backwards, right? So that would be the opposite of 20 to 24 of f of t dt, which would be 48 plus 60 plus 36, and then of course minus 36. So you see how those two are going to cancel each other out as you are doing the problem, and you're still going to end up with the same 108. So the B value does not have to be in between the beginning and the end. The important thing when you're setting these up is to make sure that you have matching values at the end of one integral to the beginning of the next integral, and it will still work out no matter how you string them together. All right, let's look at the third property of definite integrals, which is also something that we've kind of already talked about with indefinite integrals as well. So we've changed the settings on our elliptical. Maybe we increased the incline a little bit, made it a little bit harder to do. And so now it's possible to burn calories at a rate that is 5 more calories per minute than what it used to be. So maybe by increasing, like, you know how you have the little dial that you can turn that makes it a little harder to pedal as you're going around on your elliptical. So we've made it a little bit harder. So the question is, still given that I have this f of t graph up here, what if I wanted to do, figure out how many calories I had burned per minute or total calories in the time span for 16 minutes. So we're trying to calculate the definite integral from 0 to 16 of f of t plus 5 dt instead of f of t. Now, think about graphically what we're doing with this. If I am taking f of t and I add 5 to it, that out, and I'm kind of just put this over here on the side. FFT plus 5 is a vertical shift up of 5. So the graph that we had above, when we take a look at it, we basically are just going to shift it up 5. So it'll go up 5, but it'll still have the same shape as it comes through. And I'm just doing a quick rough sketch of it based on what we had. Okay, but it's going to shift it up. So there is this additional amount right here that is going to be the shift up of 5 from what it was. So remember that when we're doing the net accumulation, it's just the area under the curve. So the question then is, what did I basically do? I just added a little extra area with that rectangle at the bottom. So we also learned that when we were doing derivatives, so this kind of goes back to the derivative antiderivative relationship. The derivative of the sum of two functions is nothing more than the sum of the derivatives. And we learned that the antiderivative of a sum is nothing more than the sum of the antiderivatives. And so what we'll see is here is that it's exactly the same thing, that the definite integral of f of t plus 5 ends up being taking the definite integral from 0 to 16 of f of t dt and simply adding that to the integral 0 to 16 of 5 dt. Now, in terms of the area, what are we adding? We're adding a rectangle area, and the rectangle area is nothing more than the width times the height. So the height is 5 times the width, which is 16, is what we're adding in. And then we use what we already had for our 0 to 16 of f of t, which was, what was that, 140 calories when we were looking at it earlier. So we had 140 calories plus the 5 times 16, and that would give us the total that we have. All right, so we would end up with 220 calories burned above the 140. So that extra 5 calories per minute that we had is going to be translate, this extra 5 calories is going to basically add 80 calories to our net accumulation that we had. Also, I just realized I never answered the question over here. I got all excited in the calculation of it, that this was a total of 1,558 calories if you want to add that in. All right, so let's take a look kind of at what property that is. So let's come down and go to our properties, and we're going to add that down as number 3. So number 3 is going to be that if I have the integral from a to b of the sum or difference of two functions, dt, that it does not matter, just like the derivative of the sum is the sum of the derivatives, antiderivative of a sum is the sum of the antiderivatives. In a definite integral situation, in an accumulation of area, we can simply take the area under the curve from a to b of f of t dt and add that to the area, or subtract from a to b of g of t dt, so that we can just split those up, and that's pretty straightforward. Okay, so then we have 2 more properties to do. So let's come back into this question number 4 here and take a look at that. So now coming back to our elliptical scenario, now we also know that unfortunately for those of us that are females, most males burn calories a little bit faster than females. So a male burns calories 16% faster than females. I don't know where this number came from. This is from the CalcMedic website, so I have no idea if this is actually true or grounded in real data, but I would assume that they've done some research on this. So their rate of calorie burn is 116% of what it was for the female. So notice that what we've done is we have adapted, we've added a scalar multiple in front of the f of t. So we're now going to do a vertical stretch of the graph. And we would like to know what happens, how many calories would the male burn, and this is for the whole 24-minute workout, of 1.16 times f of t dt. So we're just adding that scalar multiple in. Now, hopefully, as you saw in question number 3, that this works very similar to the derivatives and antiderivatives that we had talked about before. So now that we're looking at a scalar multiple, hopefully you'll be like, hey, I remember that that's just a rider. That when you take the derivative of a function that has a scalar multiple in front of it, 5 times x, the derivative is 5 times 1, the derivative of x. Then it just rides along, both forwards and backwards. So the scalar multiple that's in the problem stretches it out, but it stretches the area by the same amount. Because what you're doing is you're just changing your height. Your height is that scalar multiple taller. And so everything that you're adding up for your sums of your areas is multiplied by that value. So we're going to be able to simply ride that along or pull that out and do the integral from 0 to 24 of f of t dt, which is really just the sum of all the areas that we had above in the chart. So we'll just go ahead and finish this out. We had the 140 that we had up to 16, and we had an additional 60 and an additional 36 that we were adding into that. And so doing our arithmetic, that's going to give us 273.16 total calories burned on the elliptical for the male versus the 236 that the female would have burned, because 236, that was the net area under f of t. All right, so let's add that to our property list down here for number 4. So if I have the integral from a to b of a scalar multiple times f of t dt, that constant is just a rider. It just rides along, and we can pull it out to the front and calculate the integral from a to b of f of t dt. Okay, and then we have our last property that we're going to do. I don't have a problem for it, but I've used it already in a previous problem. So, but I think it's common sense as well, that the last property is if you start at A and you don't go anywhere of any function, how much area have you accumulated? Well, if you haven't moved, then you've accumulated no area. And so the integral from A to A of f of t dt is simply going to be 0. All right, so that finishes up our discussion of the integral properties. So you're going to come down, and remember, you're going to hold off on all those handouts that are practicing FTC until after you do the 6.7 video. So you're going to do this, check your understanding, and then go to the homework discussion for that. And then we're also going to continue on to the 6.7 notes and finalize that. And then for the end of the week, you're going to be working on all the FTC practice. All right, so that's the end of this video, and we'll get those uploaded for you.